Let's start. So hello, everyone. My name is Eyad Magdy Shahin. I'm a master's student from the American University of Sharjah, and I'm attending this conference to present my research work.
Sorry, could you more loud speak because even I am not hearing you.
Okay, I'm sorry. All right. So I would like to start by welcoming the audience and thanking them for taking the time and to come to attend my presentation. And also I want to thank the team members for helping me arrange the presentation. So my research work is titled The Mechanical Performance of Sustainable Polyethylene ECC Using Dune Sands and Ggbs. I know there is complicated terms here. We will break it down as we go in the presentation. So first of all, what is ECC? ECC is short for Engineered Cementitious Composites. It's simply a high-performance type of fiber-reinforced concrete. So what is fiber-reinforced concrete? Fiber-reinforced concrete is simply concrete, the most popular construction material we know, and we add to it fibers. And this composite, we call it fiber-reinforced concrete. Now, for the concrete composition, it typically consists of a mix of materials like cement, sand, water, and chemical admixture. Those are the raw materials of concrete that we use. And then the fiber composition, we use small filaments or pieces of metals like steel, for example, or polymers like polyethylene, polypropylene, or polyvinyl alcohol. And these materials have great tension properties. And when added to concrete, which is weak in tension by nature, so it enhances the tensile properties of concrete. So we would have a composite that is a strong in tension and compression, which would enhance the structural integrity of our structures. So the function of such materials, the ECC or the FRC, it's to offer unique mechanical properties and especially high ductility. So what do we mean by ductility? Ductility is the ability of a material to deform under high loads. So if your material deforms more under high loads, then you have a ductile material, which is very beneficial in construction materials. And we have another advantage, which is damage tolerance. So what do we mean by damage tolerance? So simply, concrete has some temperature or shrinkage effects, which create some cracks on the surface of concrete. These cracks open the way for water to go inside and attack steel rebars or steel reinforcement. And this would deteriorate the structures, making the steel rebars has section losses, and it will reduce the structural integrity of our members. So this chart, I summarized the development of ECC. So how everything was started. Everything started by the year 1960. Researchers were keen to understand the effect of adding fibers to concrete. So they wanted to increase the crack resistance of concrete, because as we said, concrete has, by nature, it goes under shrinkage effects or temperature effects, which create cracks on its surface. So by adding fibers, we will reduce such effects because fiber have what we call fiber bridging effect or mechanism. This mechanism works by attaching the concrete particles together, preventing the concrete from creating white cracks. So we would have a very tiny cracks. It will prevent water from going inside and attacking our steel rebars. By the year 1970, we started to see the first applications of the fiber-reinforced concrete. We started to see fiber-reinforced concrete in precast products or shortcrete operations and also pavements. Then by the year 1980s, we started to have a more controlled way of designing FRC. We started to develop some mathematical models in order to tailor the components to our benefits. And then by the year 1990, we had the first micromechanical model. This is the first design pieces we had in this area for the fiber-reinforced concrete. It was developed by Dr. Victor Lee, a very famous pioneer in this area from University of Michigan in the United States. And then after that, we had the distinction of ECC from FRC. So we started to understand the material more. ECC would fail under what we call strain hardening, and FRC fail under what we call tension softening. I will explain this in detail in the next slide. Then by the year 2006, we had the first type of ECC. We call it M45. This is the first ECC formulation that was published. And then after 2006, we had a lot of variations on this formulation. It came by other researchers in efforts to enhance the properties of ECC into more properties. So in this chart, I'm summarizing the performance of each type of the material. First of all, we have three materials. This is conventional concrete without any fibers. This is fiber-reinforced concrete, and this is ECC. So ECC is simply an advanced version of fiber-reinforced concrete. So for example, if you would take a sample in the year 1960 and test it, you would expect a failure curve like this. This is the stress-strain curve, the tensile stress-strain curve. So let me explain it. First of all, how do we perform this test? we would take what we call a dog bone sample. Dog bone sample is simply a sample that looks like the dog bone, okay? And then we would place it inside the tensile machine with 2 clamps at the top, 2 clamps at the bottom. One end is fixed and the other end is moving. So we start to move the bottom end, and then we measure the ability of the material to take tensile forces. So for example, for conventional concrete, we would have the load keeps on increasing under it reach the failure point, and then we have a vertical line. This vertical line means the material is brittle. It doesn't have any ductility. So that's denoted by the vertical line. For the FRC, we would have a more gradual decrease. This is denoted by the effect of the fibers. When we add fibers, we will start to have better ductility. Not like ECC, but at least it's better than the conventional concrete. As you can see, ECC has a significant advantage in the crack control and the ductility behavior. As you can see, we keep increasing the load until it reaches this point, and then we have a gradual decrease. So ECC would have more ductility capacity and higher strength capacity as well. Okay, so let's move to the problem statement. So what are we testing in this research? What are we doing exactly? As I mentioned in the title, we mentioned that we are doing mechanical performance of polyethylene ECC using Dune sands and Ggbs. So these are the 2 main materials we are focusing on. Now, why are we focusing onto these materials specifically? Because the M45, the first ECC formulation, it utilized 2 materials as a primary materials, silica sand and fly ash. So these materials are great materials, but they are expensive. They are not available like Ggbs, for example, or Dune sand. In the Middle East regions, in the United Arab Emirates, and the other countries in the Middle East, we have abundance of Dune sands. So why not using it in such formulation? We would save a lot of transportation costs and a lot of other treatment processes that silica sand undergoes. For the Ggbs, we are trying to include it at a higher content compared to the other ECC mixes to promote sustainability in construction materials, and we would have more sustainable construction materials. So for the objectives, we want to design economical ECC mixture using locally sourced materials. What do I mean by locally sourced material? I mean Dune sands. And for the second objective is to improve the environmental sustainability of ECC by substituting cement with high volumes of Ggbs. So for the experimental program, we designed 3 mixes. Each mix incorporates different percentage of Ggbs as a replacement to cement. Okay, so let me explain what is Ggbs. Ggbs simply stands for ground granulated furnace ballast slag. So what is that? This is a byproduct of the steel and iron industry. So these are like a waste materials. We are not using it anywhere. So why not using it in concrete? And researchers have proven that using such materials can be a great alternative to cement, which causes CO2 emissions, and then we would have global warming and other issues attributed to that. So Ggbs has a great advantage when incorporated in such mixes. So what we are trying to do here, we are fixing all the other components. We're just changing these 2 components, the cement and Ggbs. And we want to see how is it changing by increasing the Ggbs content in the ECC formulation. Will we get higher compressive strength? Will we get higher tensile strength? Or it will be the opposite. Also, for the type of fiber we are using a polymer type of fiber, polyethylene. Now, as you can see, this type of fiber has great tensile strength of 3,000 megapascal. I want you to imagine that conventional concrete can have like 1 megapascal in tensile strength. So this is 3,000 times greater than the conventional concrete. That's why we are including fibers as a tensile reinforcement in concrete. And these are the materials we are using here: cement, Dune sand, Ggbs, silica fume, and polyethylene fiber. Okay, so we are doing 2 main tests: compression test and tensile test. How are we going to perform such tests? With the help of this machine. This is what we call the hydraulic compression machine. So let me explain how this machine works. The upper part is fixed and the bottom part is moving. So you can place your specimen. So you have the ability to use 2 specimens in this machine, either a cylinder or a cube. Cube comes in the dimension, for example, of 50 by 50 by 50 millimeters, or the cylinder can come in 100 meter diameter by 200 meter height. So you can use either of these 2 specimens. So what would happen we would place our specimen here, and the bottom part will start to moving upwards. And once it touches the surface of the upper part, now we are ready to do the test. Sorry. So once the test starts, it measures how the material would handle compression forces before it fails. So we can extract information from the machine, like forces, the peak load in kilonewton, and then we would divide it by the area, cross-sectional area of the specimen, and then we would get the compressive strength in megapascal, Newton over millimeter squared. And we are using a load control rate for this machine. So this machine moves at a 0.5 kilonewton per second. You can change this load rate based on your material. If you have a high performance material, then you can increase the rate, for example, to 1 kilonewton per second. The other test we are conducting here is the direct tensile test. So this test, as I mentioned earlier, it uses the dog bone shape of specimen. In the previous years, they used to have a thin prism to test intention. The disadvantage of such specimen design is that we have more material loss. So here we are trying to cut these parts in order to reduce the material loss in testing, and also we would get the same results. So as you can see, we can fix the upper part here, the bottom part here in these two clamps, and we can install some LVDT readings to measure our deformation, to measure how the material can deform under tensile forces. And then you can have extract information from the machine that shows the stress values and strain values. You can draw the stress strain curve. These are the dimensions in millimeters for the dog bone sample. And we here are using the displacement control rate of 1 millimeter per minute. It's different than the load control rate in the compression machine. Now for the results and discussion. So in this table, I'm showing the samples. So G30 refers to the sample that incorporating 30% Ggbs only. And G60 would incorporate 60% Ggbs. G90 would incorporate 90% Ggbs. And you can see we are having 3 samples per each mix to take the average value and compare it at the end of the day. So these values were extracted from the machine. So the machine gives you the peak loads at which the specimens fail. And then we would have the masses also. You can measure that before doing the test. And then you can have the stress. So how can we determine this stress, for example? You have the load 159 kilonewton. You divide it by 50 times 50, which is the cross-sectional area of the cube. And then you would have the Newton, kilonewton per millimeter squared. You can convert it later to Newton per millimeter squared. And this is what we call megapascal. So this is the unit used for stress measurements. After that, you can take the average of the 3 values here, and then you would have a better understanding of how the G30 mix perform under compression. For example, in this 3 mixes, we can see that G60 performs the highest of 72.5 megapascal compared to G30 at 69.9 megapascal and G90 at 62.9 megapascal. So what can we draw as a conclusion from this table? We can draw as a conclusion as while we are increasing the Ggbs level up to 60%, we can get an extra addition value in the compressive strength. However, beyond that point, we would get a decreasing value at 62.9. So the bottom line here is to choose the G60 mix in your construction applications. We have a similar table here for the cylinder type of specimen. Also the same thing, we have the peak load extracted from the machine. We would divide it by the cross-sectional area, and then we will get the stress in megapascal. It also follows the same pattern. G60 achieves the highest, then coming at G30 62.7 and G90 at 55.7 megapascal. And this is some of the curves extracted from the machine. So as you can see here, this gradual decrease denotes that we are having ductility in our specimens. We're not having vertical line like the graph I showed in the earlier of this presentation. So this would implies that ECC is a more ductile material compared to conventional concrete. Similarly, for the tensile test results, we're having 4 samples. This G30 has 5 samples, then G60 has 4 samples, and G90 4 samples. And then at the end of the day, we take the average of these samples. So similarly, we get like a column of peak load. I'm not showing it here, but we get it, the peak load in kilonewton from the machine. Then we take this load and divide it by the cross-sectional gauge length of the dog bone specimen. So let me explain that. So as you can see here, this is the part we are interested in. The machine would give you, for example, 150 kilonewton. So what are you going to do with this value? You are going to measure the cross-sectional area of this part of the dog bone, which here is 30 millimeters times, we have the thickness 15 millimeters. So 30 times 15 will give us 450 millimeters squared. This is the cross-sectional area which we will use to determine our stresses. So if you get, like, for example, 150 kilonewton, you can divide it by 450 millimeters squared, and this will give you the value in megapascal. So this is how I determine these values. And we can see the pattern here is different from the compression values. So here in the tensile strength, we're having the greatest tensile strength for G30, followed by G60, and then at the end of the day, G90. However, if we look at the strain, and the strain gives us indication about the ductility of the material, we can see that G60 achieves the highest ductility at 3.066% strain. This is higher than the G30 and higher than the G90. So this also, we can draw a conclusion from this table that G60 performs the best when it comes to ductility and strength. If we want a balance between these two properties, then G60 would be the better option here. And these are the graphs that are extracted from the machine. Now, you may wonder, why do we have a lot of drops and peaks in this graph, for example? These drops denotes the strain hardening behavior of ECC. What do we mean by strain hardening? So ECC fails under multiple cracks. It doesn't only have one crack. It has multiple cracks, and these cracks keeps on forming while we are testing the specimen. So these cracks, they enhance the ductility of the specimen. It would give it more time to handle loads before it fails at the end of the graph. And as you can see, so we have the best ductility goes for G60 again at almost 5% of the strain value. Now for the conclusion, so what are we getting from this research? We're getting that the impact of Ggbs replacing up to 60% of the Ggbs to cement would improve the ECC performance without compromising the compressive strength or the ductility. And then we can see also impact of Dune sand. ECC with Dune sand offer an equivalent alternative to the silica sand, and this would enhance the environmental practices and structural longevity. These are some of the references I used in this research, and thank you for listening.